Okay, in the previous class, we have discussed discrete wavelet transform. So we have seen that there is a filter bank structure for analysis and synthesis. So in the analysis side, you have a signal. Suppose you have an input signal S. So you process it through a series of filters H0, H1, and then you downsample it by a factor of 2. So you get approximation coefficients at level 1, and the output of this high pass filter is detailed coefficients at level 1. Then these approximation coefficients, they are again processed using the same filters H0 and H1, again downsampling by a factor of 2. So you get approximation coefficients at level 2 and detailed coefficients at level 2, so and so on. Okay, this is analysis side. Which is called as discrete wavelet transform. And then we have inverse transform for that, in which we first upsample the approximation and detailed coefficients at level 2 and then pass them through a filters G0, G1 and add them together. You get a estimate of approximation coefficients at level 1. Okay, and then further this is again upsampled, this is again upsampled, okay, processed through the same filters. So add them together, you get reconstructed signal as cap. Okay. So this is my synthesis part, or we say this is DWT and this is IDWT. Okay, so here the signal processing or this wavelet, this plays a role, in between. Okay, here. So if you just decompose the signal into approximation and detailed coefficients up to some level, suppose n, and then you just apply the output of this analysis filter bank as input to the synthesis filter bank, your output should be exactly the same as the input. Okay, if you do not have any modification. But the main part is that, okay, once you decompose the signal into different components, details and approximations, and then we modify these coefficients. Okay, by modifying these coefficients, you can remove the noise from the signal if it is a noisy signal, or you can compress the signal. This is how signal compression and signal denoising is done using the wavelets. Okay, so the algorithm for this is that, okay, you have a signal, you have a function or a signal, suppose as you decompose this signal, as using DWT up to some level, suppose n. Okay, it may be level 3 or level 4, whatever you want. And for this, you have to choose a mother wavelet. Okay, so you have to choose a wavelet and then you have to choose a level, and then you have to decompose this function or signal s up to level n using that wavelet. Okay, so how it will be decomposed? So you start from this signal s. So in the first level, you decompose this signal into two parts. Okay, so you have approximation coefficients at level 1 and detailed coefficient at level 1. So this is obtained by low pass filtering and decimation, and these are obtained by high pass filtering with decimation. Okay, so this is again further decomposed into two parts. So you have detailed coefficients at level 2 and approximation coefficients at level 2. And and if you go up to suppose level 3, so this is the coefficients, this is at level 1, then this is at level 2. So at level 3 you will decompose again A2 into two parts, that is D3 and A3. So this is level 3. Decomposition is up to level 3. Okay, so you can decompose it to level 4, whatever you want, depending upon the length of the signal itself. So you have a signal, so you choose a mother wavelet and a level, and then you decompose this signal up to that level using the wavelets, and then we apply a threshold on detailed coefficients from level 1 to level n. So this d1, these coefficients d1, d2 and d3, not on a3. Okay, so finally you have a3 left. After the decomposition you will have one approximation coefficients a3, rest are detailed coefficients d1, d2 and d3. Okay, so after you decompose the signal into different you can say levels, then you apply some threshold on the detailed coefficients starting from level 1 to level n. That is, you apply a threshold here, you apply a threshold here, you apply a threshold here. So applying threshold means you set some value, and if the coefficient is below that value, so that is simply set to 0. Okay, that is hard threshold. There is another way to call the soft threshold also. So once you apply this threshold, and how this threshold is chosen, that depends upon that for which application you are basically using for the wavelets. Okay, but this is the procedure. Okay, after decomposition you have to choose some threshold lambda. Suppose lambda is 0.2. It means all the coefficients in d1 which are below 0.2, they will become 0. Okay, so you may have the same threshold for all these levels, or you can have a level dependent threshold. Okay, so that is a different thing. So once you apply the threshold, and then finally you reconstruct using IDWT from modified coefficients. Okay, so you decompose the signal up to some level, suppose level 3, and then at the detailed coefficients you apply some threshold, so these will get modified. Your d2, d1, d2, 3, 3. So these vectors, they will not contain now the original coefficients, their coefficients will get changed. And then you apply the synthesis filter bank or inverse discrete wavelet transform to get the output signal. So this output signal will be with either it will be a denoised signal if there is a noise in the input signal, if your input signal is some original signal plus noise. Okay, so generally these noisy components, they are captured by these detailed coefficients. Okay, so if you apply a threshold, or if you make these coefficients equal to 0, it means somehow you are removing the noisy part from the signal. Okay, so signal will be noise free, output signal. Or if we or in other sense you can say, okay, if you have signal, if you decompose the signal up to some levels, and then you have made some coefficients equal to 0, which for which the amplitude is very less, so you have a data which is now in the compressed form, so it's a data compression also. Okay, so this mechanism, this method is used for signal compression and signal denoising based on this wavelets. Okay, let me show you an example. 1 minute. Okay, this is a original signal S, and this is the noisy signal, so some random noise is added to it. Okay, white Gaussian noise. So the purpose is to estimate this signal from this noisy component. Okay, so this is how we get the denoise signal using this DWT. Okay, and how you get this? You decompose this signal to some level. You have details and then approximations. And approximations are, you can see this is approximations and details. Then approximation at level 1 is again further decomposed into details and approximations. Then details and approximations. So suppose you decompose up to level 3 this signal, and then you apply a threshold here, hard threshold. So some coefficients you have made 0, and then you apply inverse DWT, you will get this signal, which is a estimate of the original signal. So you have improved the signal to noise ratio in this case. Okay. This is how wavelets are used for denoising. So denoising is a very important application of the wavelets for biomedical signals. Even if you see ECG signals or EEG signals, okay. So if they are corrupted by power line interference, or if there is some EMG noise, electromyogram noise, so that is somehow removed by this wavelet transform. Now, apart from this, you can also apply these wavelets on images. Okay. So the signal input signal S is not one dimensional. If it is a two-dimensional signal, that means if it is an image, so you can have the same filter length structure for implementation of two-dimensional discrete wavelet transform. Okay, and what we do in the images, we start from an image, suppose as, okay, so image is now a matrix. Okay, it is a matrix having some pixel intensities. Okay, so it is array of pixels, nothing else. If it is a grayscale image, depending upon whether it is, suppose if it is 8-bit, if it is a 8-bit image in grayscale, so a pixel intensity is varying from 0 to 255 to the power 8 minus 1. Okay, so this in that case gives you the black intensity, this is the white intensity, and in between we have a variation in the intensities. Okay, so yeah, somehow you may have, this is a 40 value, this is a 100, this is 250, this is 2, and so on. So we have an image here, okay, which is basically matrix or area of pixel intensities, grayscale. If you have a RGB image, in that case you will have 3 matrices. Okay. Now if you apply discrete wavelet transform on this two-dimensional DWT, you can say. So how we apply? In the one-dimensional DWT, what we have done, we have a signal. So we applied a filter on the signal and then we have decimated it. So we got this approximation and the detailed coefficients at level 1. So signal is decomposed into 2 parts at each level, approximation and detail. So this approximation is further decomposed into then A2 and A2 and so on. Now in the two-dimensional case, what we do, you have a signal as, you first apply these filters along the rows. Okay, so one row of this matrix, it is taken as a one-dimensional signal. Okay, so we have same filters H0 and H1. Okay, so you apply these filters along each row. It means this matrix, output of this, and the output of this, you will have a matrix, another matrix of the same order, isn't it? If suppose you have a 16 cross 16 matrix here with 256 pixels, so you apply this low pass filter on this row, then on this row, on this row, and so on. So you get again a 16 cross 16 matrix here. Okay, where these rows, now they are the filtered. This input row is filtered with this filter, convolution with this, you will get these elements. Similarly, you process this row using a high pass filters, At the output of this, you get another matrix of same size, 16 cross 16. Okay, now these are elements, they are basically the convolution of the rows of the original signal with this filter H1. Okay, and then we decimate it. Okay, so as we apply the filter along rows, you can say like this. So this is H0n applied on rows, H1n applied on columns, and then we decimate it by factor of 2. Now this decimation is basically decimation of columns. Decimation of columns. It means you only, after this, you only retain the even indexed columns. So you apply the filter on rows, then you remove the columns. So you retain this column, then you delete next column. Then you retain this column, you delete next column, and so on. So one column is deleted. Okay. So if you have 16 rows and 16 columns, now we'll add the output of this, you will have only 16 rows and 8 columns. Okay. So it is decimation along the columns. First you apply filter on the rows, then decimation on the columns, and then after this, now we process these images using the low pass filter, the same low pass and the high pass filter, but now they are applied on columns. Okay, so this is again the low pass filter and high pass filter, but not applied on rows, applied on columns, column filters. And then you have to decimate the rows. This is decimation along rows, this is decimation along columns. Now decimate rows means you will keep only half of the rows. So you have a suppose 16 cross 16 matrix here. At the output of this, when you apply the filter on rows and columns, you get here and here the same matrix 16 cross 16. Now when you decimate the columns, you retain only half of the columns. So you have 16 rows and 8 columns, and 16 rows and 8 columns, and then you apply this filter on the columns and then decimate the rows. So you will have now here a 8 into 8 matrix, 8 into 8 matrix, 8 into 8, and 8 cross 8 matrix. Okay. It means the 16 cross 16 matrix that you have, when you decompose this using the DWT, so we decompose this matrix into 4 matrices. Okay, so this matrix is called as CA1, approximation coefficients at level 1. This is the output of low pass and low pass. Rows also pass through low pass filters, columns also pass through low pass filters, or we sometimes write it as LL band, low pass, low pass. Then we have LH band, HL band, and HH band. Or we say it is detailed coefficients along the horizontal direction, detailed coefficients in the vertical, and detailed coefficients in the diagonal direction. Okay, so this is level 1 decomposition. So you decompose the image into 4 parts at level 1. Now at next level, you again decompose this image into other 4 parts. Okay. So then at level 3, this approximation is again further decomposed into more 4 parts and so on. This is how DWT is applied on the images. Okay. So starting from one image, this is the original image S. If you apply DWT, two-dimensional DWT at level 1, so at level 1, you decompose this image into 4 parts. Okay, so these are approximation coefficients. Rest are details. So at next level, this is level 1. At level 2, you will now decompose again this approximation coefficients into under 4 parts. So this is now approximation at level 2. These are detailed as level 2, these coefficients. Okay, if you go to level 3, so these approximation coefficients are again decomposed into 3 parts and so on. This is how DWT is performed on images. And again, when you want to denoise the image or you want to compress the image, you have the same mechanism. So you apply discrete wavelet transform on image up to certain levels, and then you choose a threshold. Okay, so certain detailed, and that threshold is applied on detailed coefficients. So make certain detailed coefficients whose magnitude is very less equal to 0. So your image is compressed. Okay, or you remove some detailed coefficients in the wavelet domain, and when you use this inverse discrete wavelet transform, so you may be able to remove the noise from the image. Okay, so see, let me take one more example. This is how this wavelet transform is applied. On the images. So this is the original image. This was the original image. So when you decompose this image up to level 1, so you have approximation coefficients, this one, and these are your details coefficient at level 1. So vertical coefficients, diagonal and horizontal. And these are the approximation coefficients at level 1. So you discard some of these coefficients because you see they contain the noisy part only. Okay. So if you delete these coefficients and you apply inverse DWT, you may remove the noise if this image is noisy. Or you may remove these parts, you may only store this much of part, your image will be compressed. Okay. This is how DWT is used for image compression. And in your this JPEG 2000 format, DWT is basically used for image compression. Okay. This is level 1. If you go to level 2, this image will be further decomposed into 2 parts. And this image will further decompose into 2 parts and so on. Okay, this is how wavelets are used for signal and image processing applications. So we will conclude now this wavelet theory here. Otherwise, there are so many more things to discuss about the wavelet system design, but we will not go into now the details. So I hope I am able to make you understand about the basics of this wavelet theory, what wavelet is and how you implement this wavelet transform using the filter banks and how you use for signal and image processing applications.